Good evening, everyone. Today, we will be covering continual learning of new diseases with dual distillation and ensemble strategy. This technical paper presentation is a part of the medical imaging course at IIT Tirupati. This particular paper was presented at the MICCAI 2020 conference on medical imaging. It will be presented by me and my friend Krishna Sumanth jointly. Let's begin with the question as to what is continual learning. With passage of time, often there's a need for the machine learning and the deep learning algorithms to be updated with addition of data or more classes so they could adapt to the ever evolving problem statement. But the problem with addition of new classes is that the model starts to forget what it had learned for the older classes with subsequent training on newer classes. This phenomena is called catastrophic forgetting. Due to catastrophic forgetting, there is a drop in the accuracy of the previous learned classes or subsequent introduction of newer classes. There's also a trade off between the bias towards the old and new classes during classification of the model. To understand this in simpler terms, let's take the example of a friend, Michael Scott, who will be playing the deep neural network in our presentation. He's like a college student who would forget everything he learned in the previous courses while focusing on the current semester. So, to put it simply, the problem addressed in this paper is making Michael learn and retain everything from his previous training on older classes as well as that on the newer classes. Before we move on, what would you do to make Michael retain everything he previously learned? Would you give him surprise tests on previous courses with overwhelming weightage in his evaluation?
We don't do that.
Instead, we understand this method developed by our friends in China and prevent our catastrophic suffering by making it retain the information using dual distillation and ensemble strategy. Before we move on to dual distillation and ensemble strategy, let's try to understand the previous methods that were proposed to solve this problem and why were they rejected. First, to understand this method in a simpler analogy, let's get back to Michael and say he has to prepare for the end semester examinations of an older course. Owing to how busy he is with the current courses, he won't go through all the lectures of the previous courses, right? Rather, he would get hold of that one friend who has made the notes and prepare only for those topics which he deems important for the exam. Similarly, in a deep neural network, we retain only those neurons in the model which are really important for the prediction of older classes and freeze their training when the new classes are introduced. The problem here is that although this can help the system keep old knowledge to some extent, it would be more difficult to continually learn new knowledge, particularly when at a later point of time most kernels in the CNN would ultimately become crucial for old knowledge. Let's take a look at the second proposed method, and to understand it, let's go back to Michael's analogy. Suppose Michael has assigned his friend Dwight to deal only with the newer classes while he deals with the older ones. This could be understood as employing another network in each stage of continual learning just for the new classes, while the original network takes care of the older ones. The problem? Suppose there is an evil professor who added questions from the previous course in the newer course exam and similarly did for the older course exam. Since both Michael Scott and Dwight Schrute can't distinguish the older image classes and the newer ones, they both failed the exam. On a similar note, the deep network would fail to classify whether the input data is from the older class or the new class and thus gives incorrect prediction when two different networks are conjugated together. So now, let's call Sumanth to throw some light on dual distillation and ensemble strategy and how it could prevent catastrophic forgetting in machine learning algorithms.
So till now, we have discussed about the continual learning and the problem of catastrophic forgetting in the process of continual learning. To save us from this misery of catastrophic forgetting, a more efficient algorithm is proposed, which is dual distillation. The dual distillation is an effective framework to keep old knowledge during learning new classes with a better way to simulate the idea of memory replay. Firstly, we'll define distillation. More specifically, what is knowledge distillation? Knowledge distillation is the process of transferring knowledge from one network which is already trained to another network which needs to be trained. In the proposed algorithm, the transferring of knowledge is happening with the help of two networks. Hence, the algorithm is named as dual distillation. In this framework, an expert classifier only for new classes is first trained by fine-tuning the original classifier of old classes. Then, the knowledge from both classifiers are distilled to teach a new classifier to recognize both old and new classes. The fine-tuning of the original classifier to expert classifier would make expert classifier largely contain old knowledge while learning new classes. Therefore, the distillation from expert classifier to the new classifier would additionally help keep knowledge of old classes. As explained and as shown in the diagram, we can see that there are three classifiers. One is original classifier, one is expert classifier, and one is updated classifier. The original classifier is trained only on the old classes, while the expert classifier is trained on the new classes. Now, the distillation happens to the updated classifier from both the original classifier and the expert classifier. Apart from distilling the knowledge from original and expert classifier, the updated classifier is also trained separately. The dataset given to the updated classifier is a large number of new classes and a small subset of old classes, which makes the updated classifier biased more towards the new classes. We can understand this in simpler terms as Michael getting an expert tutor for himself for whom he can learn new subjects and finally perform well. But won't him getting expert attention in newer subjects and frequent exercise on the older subjects make his performance a bit biased towards the new subjects? Obviously it would. To overcome this problem, an ensemble strategy is proposed. An ensemble strategy is something which is performed in the testing phase. The ensemble strategy remembers the performance of the original model with the help of exemplar representation in the previous continual round and uses it for the prediction of specifically older classes by taking the average of the older prediction probabilities with the newer prediction probabilities and uses this new average for classification. Analogous to Michael's case, suppose Michael has now the soft copy of the notes in his smartphone of all the previous courses, but only the topics which he encountered in the previous semester. Although he is continually learning the new courses from his expert tutor and is well versed with it, whenever a question on the previous topics arises, he can just look up to his notes from his phone and get some inference so as to how he shall tackle this question. This inference is like averaging his current deductions on the problem and the hint he got from this previous response on similar courses in the last sem. Come to think of it, if we have to revise some previous course for our placements of a quiz, the questions and solutions for that course gives us a pretty good revision, right? Michael is very happy with that and he would do very well in his exam. Now let's focus on the loss functions and the training part of the network. As mentioned earlier, there are three classifiers for the network: the original, the expert, and the updated classifier. Accordingly, there are three loss functions for the algorithm. One is distilled cross entropy loss between the original classifier and the updated one, which is represented by LO of theta, in which theta is the to be learned parameters of the updated classifier. In the loss function LO of theta, Pij is the modified softmax operator for the old classes, and Pij hat is a modified softmax operator for both new and old classes. On the similar lines, there is another distilled cross entropy loss between expert classifier and the updated classifier, which is represented by ln of theta, in which Qij is the modified softmax operator for new classes, and Qij hat is the modified softmax operator for both new and old classes. Along with these two losses, there is another loss function which is purely dedicated to the updated classifier, which is represented by Lc of theta. Lc of theta is the cross entropy loss for the updated classifier, in which Yij is the jth component of the one hot class labeled Yi, and Yij hat is a jth output of the updated classifier for the input image. And finally, the complete loss function is the combination of these three loss functions with the weighted sum of these three. The datasets used for the analysis for the proposed algorithm are CIFAR 100, SKIN 40 and SKIN 8. The dataset SKIN 40 consists of 40 classes of skin disease images collected from the internet with 50 training images and 10 test images for each class. For CIFAR 100, 5, 10 and 20 new classes were added for every iteration of the continual learning. And for SKIN 40, 2, 5 and 10 new classes were added for every iteration of the continual learning. And SKIN 8 dataset, the two classes were added for every iteration of the continual learning. Now let's discuss the results for the proposed network. The figure shows the proposed method outperforms all the strong baselines when classify continually learn either 2, 5 or 10 classes every time on the SKIN 40 dataset and SKIN 8 dataset. Note that the first three figures are for SKIN 40 and the last figure is for SKIN 8. We can observe that the rate at which the accuracy falls down by adding the new classes for the proposed algorithm is less compared to other classifiers. We can observe one more thing, that in the last figure there is a less improvement for the SKIN 8 dataset compared to SKIN 40 dataset. This is due to the fewer classes in SKIN 8 or the fewer rounds of the continual learning. To check the robustness and the generalization of the proposed algorithm, the performance comparison was done with different CNN backbones. The average and the standard deviation of the accuracy at the end of the continual learning of 5 classes every time is reported in the table. The three different CNN backbones were ResNet 18, AlexNet and VGG 19. We can see that with ResNet 18, we can get the highest accuracy. So here are the implementation details for the proposed framework. As explained earlier, ResNet 18 was employed as the backbone CNN. Stochastic gradient descent optimizer was used to optimize the network, and the batch size used was 16. Initially, the learning rate was set to 0.01 and then divided by 10 at the 80th and 160th epoch respectively, with a weight decay of 10 power minus 5 and the momentum of 0.9. Each model was trained up to 200 epochs.
In this study, we proposed a new continual learning framework to help intelligent systems reduce catastrophic forgetting of old knowledge during learning new classes. Experiments showed that dual distillation from two teachers can help teach a new classifier more effectively during continual learning of new diseases, and the ensemble prediction from the old and new classifiers further alleviate the forgetting of old knowledge. I would like to thank Professor Lee and Zuan who came up with this idea of continual learning, which made this presentation possible in the first place. Finally, I would like to thank Sumanth, our dear friend Scott, and all the people who made this presentation possible.
Live long and prosper.